Hello everyone, welcome back to this video series on one-dimensional potential flows. So in today's lecture, we will first derive the differential equation of one-dimensional potential flow. So once we are done with the differential equation, then we will reduce it to the weak form. So once you have got the weak form of the differential equation, what we can do is we can come up with the finite element formulation. So that is the agenda today. If you're well acquainted with the differential equation of one-dimensional potential flow, you can directly go to the weak form part. But I'm just going to derive the differential equation just to set the stage nicely. I'm just going to derive the differential equation for one-dimensional potential flow. So just imagine that there is a pipe through which fluid is flowing. For some reason, I'm just going to make it rectangular in cross-section. The reason why I would make this rectangular in cross-section is because it becomes easy for me to entire the coordinate axis. For example, I can call this as x. This can be my y, and this can be my z. Okay, so let me represent the fluid flow. So just imagine that fluid is flowing through this pipe from the left side towards the right side. It is a potential flow, which means that the difference in pressure, probably the left side has more pressure compared to the right side. So the difference in pressure is what is driving the fluid. Now, what I'm going to do, I'm going to consider two cross-sectional areas. This is my first cross-sectional area. I'll be writing the equation for the total quantity of fluid, mass flow rate through this cross-sectional area. And this is my second cross-sectional area. Okay. Now, suppose if I'm considering a small fluid particle, say for example, I'll call this particle, let me give you a name to this particle. I will call this Alan. Now, in the case of a one-dimensional fluid flow problem, if Alan is going to take 3 steps towards the right side per unit time, then all the particles above and beneath Alan, they're also going to take the same 3 steps per unit time. All right. So if Alan is going to take 3 steps, then all the particles along the z direction, okay, they are also going to take the same 3 steps, which means that this term velocity, it is a function of only x-axis, because all the particles along the y direction and all the particles along the z direction, they are going to take the same number of steps per unit time as Alan. So we can say that velocity is a property of only one direction, that is x direction, which means if I am considering another particle onto the right side, so if Alan is taking 3 steps, maybe we will call this yellow guy Raj. Maybe Raj is not going to take 3 steps. Probably he's going to take 5 steps. Just an example. So velocity, clearly it is a function of x-axis only. So that is what makes this problem a one-dimensional problem. Okay, now I'm going to write an equation for the quantity of fluid that is flowing through the first cross-section. So let us try to write the quantity of fluid that is flowing through the first cross-section. So this is our first cross-section. This is our second cross-section. Simple, the equation is rho AV. So rho density, A for the cross-sectional area, and V for the velocity. So that is the quantity of fluid that is flowing through the first cross-section. And the quantity of fluid that is coming out of the second cross-section. It should be the same quantity of fluid for incompressible flow that should come out of the second cross-section But let us say the quantity of fluid that is coming out of the second cross-section is rho AU, plus let us say there is some change. We don't know how that change comes, but we will assume that there is a small change in the quantity of fluid that is coming out, plus rho AU. Since I am putting a plus sign, you may think that there is a gain. If I'm putting a minus sign, that can be a loss. So in general, I will just put a plus sign, okay? Divided by del x multiplied by del x. So I'm not going to do any damage to this equation. So this is the quantity of fluid that is coming out, and this is the quantity of fluid that is coming in, okay? There is a small change. So the difference is the quantity of fluid. The difference between the two is going to tell us the quantity of fluid that is actually stored between the two cross sections. All right. For example, if 5 is coming in and only 3 is going out, the remainder 2 is stored or it is going into the sink. Okay. So what is the difference? The difference is rho AU plus del of rho AU divided by del x into del x minus rho AU. That is equal to either gain or loss, which means either the fluid is going into the sink, in which case it is a loss, or there is a source that is pumping some extra fluid between the two cross sections. In that case, it will be a gain. Or if it is an incompressible flow and there is neither source nor gain, then this should be equal to 0. So we will say that this is an incompressible fluid flow. So this should be equal to 0. The next step, it's going to be, okay, I can say that it is an incompressible fluid flow, so I can pull the density terms common outside. I can divide by density on the left side and the right side. So I can get rid of density at this point of time. And I can also say that these two terms will go away. So since the difference del term, if it is going to be very small, I will get dou AU divided by dou x into dx is equal to 0. I can pull the density term outside, so I can divide by density on either side so that the density term disappears. I can, if the cross-sectional area is constant between the two cross-sections, so I can also pull the cross-sectional area outside. So it will be dou A into dou U by dou x. Take this dx also to the right side, so that also disappears. That is equal to 0. So that's our differential equation. Now, you may ask this question, why the area is not taken to the right side? If it is a constant cross-section throughout, you can take it to the right side. But when we do the finite element formulation, we will be dealing with situations where the area can actually change. Okay. Maybe you are going to encounter a tapered section. So in that case, because the area changes, then it would be a good idea to keep the area with you so that you can come up with the finite element formulation. You can use the trick of finite element formulation. So that is A into dou U by dou x is equal to 0. Now, between the two cross sections, so this is our first cross section, 1, and this is our second cross section. Okay, this is our second cross section, 2. Let us say that the pressure in the first cross section, let me denote that as phi 1, and the pressure in the second cross section is phi 2. And let us say that phi 1 is greater than phi 2. Then the difference between the pressure, which is d phi divided by dx, because they are separated by a small distance dx, is what is driving the fluid velocity. So the velocity should be proportional to the difference in the pressure. So if you want to eliminate the proportionality sign, you have to introduce a constant. So I'll introduce a constant k into d phi by dx. In ideal case, the value of k is equal to 1. But suppose between the two cross sections there is a permeable, there is a there is a layer, or maybe there is a permeability layer that is actually going to hinder the fluid flow. So in that case, the value of K should be less than 1. If the value of K is equal to 0, then there is no fluid flow. Okay, if K is equal to 0, there is not going to be no fluid flow. So no fluid flow. So ideal case, the value of K is going to be equal to 0. So you could see that K is related to permeability. So what I will do now is I will take this value of U and whatever governing differential equation that we have derived, I'm just going to plug it here. So mathematics is just like moving objects. So you can take the value of U and you can plug it there. So let us see what comes. So it will be A into dou U by dou X. If you just plug that value, it will be dou by dou X into the value of U is K into dou d phi by dx. I think I can use d phi by dx, d by dx, because it is a one-dimensional problem. It is equal to 0. So in the next case, it will be A into K is a constant. I can take it outside. It will be d squared phi by dx square is equal to 0. So that is my differential equation. So I'm going to derive the weak form of this differential equation. So first I have to write what is Galerkin's weighted residual method. It is integral of Wi into capital R into, for a one-dimensional problem, it is dx, it is equal to 0. So in the description, I will give you a link and you can check what is the physical meaning of this Galerkin's weighted residual method. So you can just check that video to completely understand what is the physical meaning of Galerkin's weighted residual method, how this method actually comes in the first place. So we know by Galerkin's weighted residual method, the governing differential equation is the residual, right? So in that case, it will be integral of Wi into capital R, which is A into K into d square phi cap I have to put into dx is equal to 0. Now, one meaning of the word residual here is that the physical meaning of residual is it is an error. Okay, that is the physical meaning of the residual. Okay, so when you assume a trial solution for phi, and you differentiate it 2 times, and you plug it here in the differential equation, then multiplied by ak, it should be equal to 0, but if it is not equal to 0, that is an error. So that is what we call it as the residual. I think in the description, in the Galerkin's weighted residual method description, I have tried my best to explain the physical meaning of Galerkin's weighted residual method. You can just check it through at your leisure. So, okay, that is our Galerkin's weighted residual method. This cap indicates that you have assumed a trial solution for phi, you have differentiated it 2 times, and you have substituted it here. Okay, so that is this is the expression for this is Galerkin's weighted residual method. In the next step, I'm going to take one differentiation outside. So let us take one differentiation outside. It is integral of Wi into A. Okay, taking one differentiation outside, d by dx into d phi by dx into dx is equal to 0. I think I missed this ak, so ak is here. Okay, that term ak is here. So this is of the form integral of u dv. So this is going to be u, this term is going to be d, and this term is going to be v. So this is of the form u dv. Okay, this is of the form integral of u dv. We will just have to substitute for u dv formula. So we have integral of u dv is equal to uv over the limit alpha to beta minus integral of v du over the limit alpha to beta. So simply substituting will get us the weak form. So let me do that. So u, it is wi V, it is ak into d phi by dx over the limit alpha to beta. But of course, we will be substituting the limits between 0 to L because we will be applying the weak form to a small piece of the bar. So it is going to be from 0 to L minus integral over the limit 0 to L v du. It is ak into d phi by dx into du. It is dwi by dx into dx. That should be equal to 0. Now I can take this term to the right side. So I'll be getting integral over the limit 0 to L ak into d phi by dx into dwi by dx into dx is equal to wi ak into d phi by dx over the limit 0 to L. So this is my weak form. So we will be using this weak form to come up with the finite element formulation. So we will do that in the next part of the video. So thank you all for your patience.